Chemical behavior is really the behavior of electrons. And if we want to understand how electrons in molecules behave, a logical starting point is to begin with the constituents of molecules, atoms. In this video series, I'm going to talk a little bit first about older models of the atom, just to give us a little bit of historical perspective, and we'll progress fairly rapidly to talking about modern quantum mechanical models. The most important concept to get from the quantum mechanical model of the atom is the idea of the orbital, and this is a concept that a lot of students struggle with. So we'll talk about the three components of any orbital: occupancy, energy, and shape. We'll see a little bit about how the orbitals of hydrogen can be calculated mathematically, although we won't go through the calculations ourselves. And then finally, we'll see how we can generalize the orbitals of hydrogen to predict the orbitals and the occupancies of those orbitals for heavier atoms as well. This atomic foundation is the basis for understanding how electrons in molecules behave. And so when you move on to more advanced chemistry classes or start thinking about the behavior of molecules, it's really atomic behavior generalized in a sense. Let's begin by talking about some old models of the atom. So you probably knew already that the atom is composed of protons and neutrons at a nucleus and negatively charged electrons that surround the nucleus. Let's look here at the hydrogen atom and take as the distance between the proton and electron the value r. Older models of the atom assumed that that distance r could take on any value. Now there's an electrostatic potential here between the positively charged proton and the negatively charged electron. They attract each other, so when they're held at a distance, there's some intrinsic potential energy there. And if that value r can vary continuously and take on any value, that means that we should expect a continuous spectrum of energies for the atom. Depending on the distance r, we could achieve any energy that we wanted. In terms of the light emitted by the atom, this implies a rainbow spectrum. As we'll shortly see, energy is inversely proportional to wavelength, and so if we can get any energy value, we should be able to get any wavelength of light out of the atom, and if we give it enough energy, we ought to observe a rainbow of colors emitted by the atom. However, this is not what's observed in practice. Instead of observing a rainbow, we only observe the emission of very specific wavelengths of light from the atom. So we see very thin lines instead of a continuous rainbow of colors. According to quantum mechanics, the wavelength is inversely proportional to the energy. Namely, the energy is equal to h, a constant called Planck's constant, times the speed of light divided by the wavelength. This can also be written as h times nu, where nu is the frequency of the light. So this seems a little bit strange. Instead of r being able to take on any old value, it appears that r can only assume very specific values. The electron only seems to be able to occupy particular distances from the nucleus. Some new models of the atom were needed to explain this, and the first one that really took hold, which was developed by Bohr, used this idea that r cannot be continuous. It can only take on discrete values. Now, and this is a theme we'll come back to again and again, the number of these values may be infinite. So the atom can assume infinite energy, but the important point is that there are finite distances between the possible r values. So r is proportional then to something like an integer n that's 1, 2, 3, 4. Notice there's a finite difference between those n values. They have to be integers. So r can only assume very specific values. However, that number of n values may be infinite. We'll come back to this again shortly. This is a phenomenon that we call quantization because the energy appears to come in little packets, or what we call quanta. You can only get energy in a certain quantity, not as small as you want or as large as you want. It has to come in certain multiples. Bohr's model of the atom used this kind of solar system or orbit type idea, where these orbits that you see, A, B, and C, are the only allowed orbits for the electron. Because the electron can only sit on these positions, that leads to an energy spectrum that looks something like this, where those orbits A, B, and C correspond to very specific energy levels. A being the closest to the nucleus is the smallest, B is a little bit farther from the nucleus, and so it's a little higher in energy, and C is the highest in energy and the farthest from the nucleus. This idea that the position of the electron is in some way quantized was really the foundation of modern quantum mechanical models. And while it was shown later that the orbits are not circular, and this is still a simplification of reality, this idea of the quantization of energies within atoms is central. In fact, if you look at the center of this slide, these atomic spectra, of course, are still valid. And really, you need only look at the atomic spectra and use the relation E equals hc over lambda to see that the energies of electrons in atoms are quantized. And this idea of quantization, this idea of the energy being proportional to an integer n that's 1, 2, 3, etc., is really central to modern quantum mechanical models.